Hi, in this video lesson for AP Physics C, we are going to look at a situation in which you have a current carrying loop that's placed inside a magnetic field that's produced by something from the outside world. And what I would like you to be able to do is to predict when a torque might act on that loop. What are the conditions for the torque in order for a torque to act on it, and also to be able to estimate how much torque acts on the loop when it's there. So let's start off with a picture of a loop here. This is a piece of wire, and it's kind of a rectangular shape. We're going to connect these two ends of the wire across a battery, and we're going to force current to flow. And why don't we just make the current flow in this direction, clockwise? And then that current is going to flow out the other end. Okay. And what we're going to look at is we're going to see if this loop has any tendency to rotate around an axis, which we're going to draw right through the middle of the loop. It's also in the plane of the loop. Okay. Let's put some dimensions on this loop. Let's say that in this direction the loop has a length L, and let's say that going sideways the loop has a width W. That's the complete distance from left to right side. Okay, and the last thing we're going to do here is put a uniform magnetic field into the picture, and we're going to make that magnetic field go from left to right. And I'll just draw two field lines there, but the idea would be that the field is filling up the whole page, and it's nice and uniform, meaning it's just going from left to right. Okay, it's heading to the right. Okay, so the first thing we want to do is ask the question, does a torque act? And so we have to remember the definition of torque. Torque is a vector, and it's a vector cross product of radius and force. And so what we're going to do now is take a look at that, and we're going to use the axis as the line that we're going to start when we measure the radius, and then we're going to see if there's any force acting on the segments of the wire that are separated by some distance. Okay. So first of all, let's look at the segment that's over here on the left side. And so I mean the segment that extends from here to here, between those 2 points. Does a magnetic force act on that wire segment, just that one piece? And let's take a look. So what we have here is a current that goes straight up, a magnetic field which is going straight to the right. And the question is there a force? So what we have to remember is that to test that, we have another cross product to consider, and that is the magnetic force, and we'll be looking at the cross product between the length vector and the magnetic field vector. Okay. So what I'm going to do is I'm going to now take my right hand, and I'm going to put my finger in the direction of the length vector. Remember, that's really just the direction of the current. So my finger points up, and then I want to face my palm in the direction of the magnetic field. So I rotate, and now my palm is facing in the direction of the magnetic field. And what this tells me is that the force does act on this segment, and the force is directed into the page. So did you notice that the thumb actually points into the page? So I'm going to draw that over here, and we'll say that the force on this whole piece of the wire goes into the page. Now, this whole piece of wire is separated by a certain distance from the axis, and the radius of that is going to be the width of of this entire loop divided by 2. Okay, it's the half width. So my torque here is going to be, yes, I have a piece here. So the torque on the left segment is going to be W over 2, and times the force that's acting, and that force is going to be equal to I times L. In this case, L is actually that L, so the L matches up with our formula here. So L is this entire length here, times B, and in this case the sine would be the sine of 90, because you have a right angle between the B vector and the L vector. And so that, of course, is just equal to 1. So on the left side, we end up with the torque equal to W over 2 times ILB. All right, let's look on the right side. On the right side, it's a very similar analysis, except now your finger is going to start off going in the negative direction, going down, because that's the direction of the current. And then your palm is going to still face in the direction of the field. And in this case, you'll notice that your thumb is pointing up. So the right-hand rule tells us that the force on this segment is pointing at us. Okay? And of course, that's also acting on a segment W over 2. So we do have a torque coming from that side. Let's write that down. So we have W over 2, and again, times I, times L, times B, times the sine of 90. And for the same reasons as before, the sine of 90 is 1. Now, something that's important for us to think about is, do these torques act in the same direction? And the answer is they do. So if you can imagine this, a force pushing down on the left side of the loop is going to cause this part of the loop to rotate away from you, correct? So this downwards force is going to cause, this force into the page is going to cause this part of the loop to rotate into the page, away from you. This force is going to pull this edge of the loop towards you. And so the effect of both of these torques is that they work in the same direction. So if you want to calculate the net torque, you would have to add together those two torques. And so if I were to add these terms together, I'm going to have, I forgot to do this, I would have W over 2 times ILB from the left torque, but I'm also going to have W over 2 times ILB from the right torque. And so my net is going to be 1/2 plus 1/2, that's W times I times L times B. Okay. Now, before I do anything else with that, you might be wondering, well, what about the top segment of the loop? What about the bottom segment? If you do a quick analysis with that, you'll see that, well, there shouldn't be any force, because the current in the top section is parallel to the magnetic field. So there is no force from the top section. Also, down here, the current is still in the same general direction as the uniform field. In other words, it's left to right. So down here, you would also have F equals 0 on both those segments. So when we're writing this formula for the net torque, we don't have to worry about the top and the bottom segments because they don't contribute anything. All right, let's then look at this result. This is important. So we have a net torque on our loop. If I were to recognize that W times L, right, width times length is actually equal to the area of this loop, I could write this in a simplified way. Okay, so A is now my area. Of course, that would be in square meters. Of course, current and magnetic field are expressed in their usual units. Okay, and so this would be the net torque that acts on the loop. I'm gonna do one last thing to this formula. I'm gonna add a couple of things here, and then I'll just justify them at the end. The final version of this formula is oftentimes written like this. And this is the one I'm going to put a box around. And what I did is I added a term n here, and that term n represents multiple loops of wire. So this would be the number of loops. So obviously, the result that I just derived, I times A times B, applies to a wire that has one single loop that goes around. But what if I want to get more torque? I might wrap this wire around and have like 50 loops or 100 loops. And the advantage would be that every time I add another loop, I'm going to increase the torque by multiplying it by that value of n. Okay, so that's where n comes from. The other thing which shows up here is times the sine of this angle phi again. And that angle phi is going to be the area between the area vector of the loop and the magnetic field. Okay. And so let's just take 1 second here and think about that. The area vector of the loop is the vector which is perpendicular to the plane of the loop. Okay, right? So I'm just going to sketch that here. If I have my loop and it's kind of sideways, the area vector would be that vector that makes a right angle to that loop. And that's what we're saying is equal to L times W, length times width. So it's a vector which is perpendicular to the plane of the loop. Now, when we add this sine function here at the end, what we're saying is that you get the most torque when the area vector is lined up with the magnetic field. So when this is the situation, when these two vectors are lined up, that's going to be a maximum torque. And when the vectors make a right angle, maybe like this, that's when your torque is equal to 0. So the torque that acts on this loop is not a constant torque. As the loop actually turns, the torque is different. I'm just going to have you think about this. If you were to rotate the loop by 90 degrees in either direction, you would actually have 0 torque. I'm going to just represent that down here. Now, I know I'm drawing the loop the same way, so it's easier for me to just draw the magnetic field either being out of the page or into the page. And we'll have current, current, current. That's going in the same direction like so. So in this situation, I hope you can tell that the magnetic field and the loop are now, they're 90 degrees different than what they were in the example that we started with. With the right-hand rule, I'm just going to show you that if you look at this section right here, if I put my finger in the direction of the current, okay, and I put my palm facing the direction of the magnetic field, it's doing that right now, that my force goes this way. The force on this piece of the segment points in. If I do the same analysis over here, I find that the force also points in with an equal and opposite value. Okay. In fact, if I do that on the top and bottom segments, I also find that the forces are pointing in. I'm running out of space, so I'll just draw it like so. And so the point is that the forces are now not only canceling each other, but the torques are also canceling each other also. So there's no torque that acts here. This is a torque equals 0 situation. The same analysis applies here. I'll let you try that. Obviously, your forces will be reversed.